Hello and welcome back to Aerospace and Mechanical Lab 1. We are going to discuss the theory of bending in torsion lab today. So today we will start by talking about bending, the theory of bending, the equations that are used for the bending and the different types of bending we can see around us. And then we are going to move on to torsion, talking about the applications of bending and torsion analysis. And we will move on to talking about the test standards, and eventually we will wrap up by talking about the bending and torsion test at the end of the lecture. So what is bending? Whenever a beam is subjected to an equal and opposite couple that is acting in the same longitudinal plane, that specific beam will experience bending. So we need to have a couple, and the couples need to act in the same longitudinal plane. We will experience bending. An example of a bending couple is like this. So you can see we have 32 Newton forces exerted on A and B, and on C and D we have two supports that are holding this beam. This will create a bending moment like this. A real world example of these type of bending systems or bended beams is weightlifting. So you have the two supports and you have the two forces that are being exerted on this beam. And then this beam is going to bend like this. Okay, how should we analyze bending? What is the governing equation for bending? Bending of a beam is governed by the Euler-Bernoulli equation, which essentially says the flexural rigidity multiplied by the fourth derivative of deflection with respect to the location on the beam has to be equal to the load. And the load can be a distributed load or can be just a point load that is exerted on a specific point. Okay, so the deflection of the beam, essentially the movement in this direction, the direction of the couple, is related to, of course, changes by location, but is related to or changes with respect to the flexural rigidity. And the flexural rigidity is the modulus of elasticity multiplied by the second moment of inertia. And all of these combined is going to be equal to the amount of load that you are applying to your beam. So higher flexural rigidity is going to result in lower deflection. That is the idea of a beam bending. Let's talk about the importance of moment of inertia for a second. Let's watch this video about the importance of moment of inertia.
The same way we did before, the beam will bend in a way that will cause the lower edge to be in max tension outside of the profile, where it is needed most. The more material further from the neutral axis, the larger the second moment of area will be. Applying that to the equation, we can see that a larger second moment of area would result in smaller deflection. So if we place this section under the same bending, it would actually be stronger if we flipped it over 90 degrees, because now more material is located further from the neutral axis. We could make it even stronger again by reducing this thickness to a minimum, just enough to resist the shear stress, and placing that material at the top, and suddenly we're back to the ideal shape. You can see this idea put into action all around. In my last video, I mentioned just one of them, when I spoke about the Willis tower using a bundled tube structure. This structure maximizes the amount of steel on the outside of the building to maximize its resistance to lateral bending from wind and other loads. I will be talking about another application of this technology in my next video, and if you can think of any other examples of the second moment of area being applied in the world around you, be sure to share it in the comments. Thanks for watching.
Okay, so the type of bending we are going to see in our lab is a three-point bending. A three-point bending is essentially where you apply a load in the middle and you have two supports at the ends of the beam. Very simple. It happens a lot in it has different types of applications. You will see it in the world around you a lot. But we are going to focus on two simplest types of three-point bending. Essentially a bending, a simply supported beam, which has these type of supports, a pin support and a rolling support, on which you can actually rotate and translate, and a built-in beam, which has two fixed supports, so no rotation, no translation at all on any of these sides. Okay, so for this type of beam, the moment distribution is going to look like this. We're going to have the maximum moment in the middle, which means that we are definitely going to have the maximum deflection in the middle. And the shear force diagram is going to look like this. For the built-in bending, the moment distribution will be a little different, meaning that the deflection in the middle, the maximum deflection you are going to experience, is also going to be a little different, but the shear force diagram is going to stay the same. Okay, so at this point we understand what bending is, and we know what type of bending we are going to see in the lab and what type of analysis we need to do on the bending. Let's move on to torsion and talk about torsion a little bit. Torsion is essentially, torque is a moment that twists a structure like this, right? So when you apply a twisting torque, you are going to twist the structure. It's very intuitive, very understandable, and it is different from axial loads because the distribution of stress over the cross section is not going to be uniform. So we are going to have a different distribution of a stress over the cross section, which essentially means that we are going to see some twisting. Torsion, the idea of torsion, is used in the industry a lot. A very famous example of using resistance to torsion, essentially, or a material that can resist torsion, is a torsion box. Using a torsion box inside the wings of an aircraft. As you can see, inside the wings we are going to have a torque that is going to twist your wing. By using a torsion box, we can reduce the amount of twisting. Of course, the twisting of a structure is not, at least on an aircraft, is not an ideal scenario for us. So we need to come up with mechanisms that can resist this. Hence the introduction of the torsion box. Okay, so, and yeah, twisting motion of the beam is called torsion. But how can we analyze torsion? Using through this equation, in which T stands for torque, so torque that you are applying to the beam. J is the polar moment of inertia, or the polar second moment of area, or the torsion constant. We also call it the torsion constant. G is the modulus of rigidity. So in the bending of beam, we had the moment of inertia, or the second moment of area, and modulus of elasticity, Young's modulus. In the twisting of the beam, in the torsion of the beam, we have the modulus of rigidity and the polar moment of inertia. And the displacement of interest for us here is the angle of twist, how much of the twisting you're going to see in your beam. Tau is shear stress that your beam experiences. L is the shaft length, and R is the shaft radius. Okay, so the idea of the test you're going to do is to find the modulus of rigidity of the beam you are testing. So essentially, and using this value for modulus of elasticity, you can identify the material that you are using for your test. Okay, let's say an application of bending and torsion analysis and bending and torsion tests on wings of an aircraft, for example. So you can see when you design the wings of an aircraft, you have to make sure that when you design the wings of an aircraft, you have to make sure that it can withstand bending load. Essentially, you have the lift force that is pushing your aircraft up. As you are aware at this point, I mean, you have done the flight simulator lab, so you know this by heart. And this pushing up of the wing might cause bending in the wing, and we don't want this to happen, or we want to be able to control it. There are different mechanisms we can employ to control the bending of the beam, but testing whether the mechanisms you have applied to your design works is very crucial. And you can see that they have this huge structure that is installed on an actual wing of an actual aircraft, and then they do the bending test. This is a huge mechanism. This is the size of our department. It might be even bigger. Sorry about the train noise. I mean, we have the train problem in Colombia. Yeah. And so an example of a bending and torsion analysis. This is very important, very crucial. You have to make sure that you test your design, you test the prototypes of your design, and also whenever you manufacture the actual wing, you want to test the actual aircraft. Of course, for safety reasons, you want your aircraft to work. Okay, let's move on. So the beams we are going to use in the lab for the bending part of the lab is just a regular rectangular beam and an I-beam and a hollow rectangular beam. So the difference between these beams is going to be the fact that their moment of inertia is different. Everything else, but again, material that we use in these beams is going to be the same. So the idea is, because of this moment of inertia, you're going to experience different deflections, but at the end of the day, you should calculate the same modulus of elasticity for all of these beams, because these are the same beam material. Okay, so what type of analysis should we do? For the simply supported beam, the maximum deflection is something that you are going to measure in the lab, and the maximum deflection is going to be equal to the amount of load multiplied by the length of the beam cubed divided by 48 multiplied by modulus of elasticity multiplied by the moment of inertia. And for a built-in beam, the equation is going to be different. Specifically, the denominator is going to have a larger value, 192. Where did we get these equations? You just have to take the integral of this general Euler-Bernoulli equation using the boundary conditions you have here. So, do we need to know how to get to these equations? No, just have to use them for your test, to analyze your test. And you have to keep in mind that you also have to do a statistical analysis on your results as well. For the torsion parts, you are going to be given a hollow cylinder and a filled cylinder, yes, and a rod, essentially, a hollow rod and a regular rod, and a different radius rod. But the thing is, all of these are going to have the exact same material, and then you're going to apply a load, torque to your system, and you can calculate the polar moment of inertia using these two equations. This is the equation for the regular rod, and this is the equation for the hollow rod. This is the diameter of the rod, the outer diameter of the rod. This is the inner diameter of the rod. Just calculate the polar moment of inertia, put it inside this equation, and you just have to measure the angle of twist, and you can do the analysis. Okay, But before moving on, this is the first time you are doing an actual mechanical test, of course, other than the hardness test. But this is the first time in which you are actually designing the test. You are changing the support and everything. So we have to know how we can actually design a test. What type of principles we have to follow. Right? The goal of this bending test for us is to measure the flexural rigidity of the beam. And we also have to know the guidelines for any other mechanical tests. Are there any guidelines? Are there any rules? Or why do we even need these guidelines and rules? The answer to all of these questions is that we do have guidelines as rules, and we do need the guidelines to make sure that the results of our tests are uniform and understandable to everyone around the world. So if everyone follows the same guidelines, all people can compare the results. You can actually run a bending test here, find the modulus of elasticity for a specific material, and compare it to the results someone has published in China, right? So for these purposes, we have ASTM standards. What are the ASTM standards? ASTM standards, formerly known as American Society for Testing Materials, is essentially is an organization whose main goal is to develop and publish test methods that everybody agrees on. For any type of test, they have a guideline. An example of any type of test is the type of test we do here, a 3-point bending test. So for these 3-point bending tests, they usually give us these as the type of material you can use for the test, the type of support, the type of load, the size of the material, everything essentially is going to be given to us. And then using this, you can design a test, run a test, compare your results with everyone's results around the world. Understanding this is very important for experimental design. Whatever experiment you design has to follow available guidelines that are out there, because whatever experiment you do, you want to be able to compare to other people's experiments. Okay, let's see an example of a 3-point bending test that is done based on the ASTM standards that are available for a concrete testing. So this is ASTM C1609, which is the standard test method for flexural performance of fiber reinforced concrete. Whenever you want to do a flexural performance, do any sort of test to measure the flexural performance of a fiber reinforced concrete, you have to do the test like this. So this is a 4-point bending. Actually, you see these two are going to apply the load using this load cell, and these two are going to be our support system. Let's really fast forward a little bit. See, so this is where we are going to apply the load. These are the supports, and we are measuring the displacement, the deflection here. And it is connected to a computer. You can measure the deflection with respect to load, which is the thing that we want to measure. So we can use the formulas we have to find or investigate the flexural rigidity of our model. Okay, so when you go to the lab, these are the systems you're going to see. You're going to see this is our torsion system. This is a very simple system. You apply the load here, you apply the torque here, and then you measure the twist using this mechanism. We have upgraded this to give us the digital angle of twist, easier to deal with, of course. And we also have upgraded this dial to a digital dial. So this is going to measure the deflection for us for different types of beams, and these are your supports. For the simply supported beam, you just have to make sure that these two are loose, so the beam can rotate, can move inside. And for the built-in beam, you want to make sure that these are as not loose as possible. Okay. The idea of these labs is for you to understand the importance of material properties and moment of inertia on bending and torsion behavior. We also want you to understand the relationship between bending, load, and deflection. The same is true for torsion, and we also want to understand the principles of 3-point bending. You have to keep in mind that all tests must be done at least 5 times, and you can share your results with your section mates, like with other groups that are in your section. The reason we do this 5 times is because I want you to do a statistical analysis and find the confidence interval, because uncertainty analysis is of utmost importance in any experimental measurement. And whenever the confidence interval is not given to you, you can use the 75% confidence interval. This is it for today's lecture. Thank you for joining us. I will also upload a video of the lab itself. And have a good rest of your day.